Hi, my name is Amy Sullivan, and I'm the current Vice President of AAAR, and it's my pleasure to welcome you to the 26th in our monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So with these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities, and also give us a chance to meet outside of the annual conference. So each month, the editors of AS&T select a high-impact paper to be presented by its author. These lectures are being recorded, and you can access them later off of AAAR's YouTube channel, which you can access from the AAAR webpage under the Events tab. In addition, our student chapters serve as the hosts for these lectures. I want to thank all of you for joining us and all of you that have helped to make these happen. And so with that, I will turn it over to our student chapter from the University of California, Riverside. Thanks.
Thank you, Amy. Hi, everyone. Good afternoon, good morning, whenever you're joining from. My name is Erin. I'm the UCR AAAR Student Chapter President. I'm really happy to see so many people here today. I know that this lecture is going to be great. I know you're going to love it because our speaker today is Dr. Benjamin Nault. It's my pleasure to be able to introduce him and his research to you. So a little bit of background, if you don't know much about Dr. Nault or his research yet, he got his bachelor's degree at the Purdue University Chemistry Department, which is a Nobel Prize winning department, very cool. And while there, he did undergraduate research with NASA. I believe that's where a lot of the interest in atmospheric chemistry came from, or at least started. And he then went right on to UC Berkeley for his PhD in Earth and Planetary Sciences, collecting field data and research aircrafts, looking into atmospheric NOx chemistry. After this, he went to CU Boulder, which I'm sure a lot of you know also has an incredible atmospheric chemistry community, working in the Jimenez group as a postdoctoral fellow. And he was looking into urban SOA sources, as well as tropospheric inorganic aerosol chemistry, and instrument development and quantification. And currently, Dr. Nault is working with Aerodyne as a research scientist in their Center for Aerosol and Cloud Chemistry, where he did some postdoctoral research. And he is additionally doing research at Johns Hopkins University in the Department of Environmental Health and Engineering. So a lot of research, a lot of good aerosol atmospheric stuff, super exciting. And his research interests now are in atmospheric chemistry and pollution, of course, and studying the sources and chemistry of gas and particle phase pollutants, how they impact air quality, and how that goes on to impact community health and well-being. And especially interesting to me, at least, is his work in developing and improving the instruments that scientists use to look into these things, to study these instruments such as the AMS and the ACSM. So this is going to be the focus of today's talk. I personally consider Dr. Nault an authority on these instruments and how they work and why they work. I've seen so many useful materials from him, so I'm very grateful for another opportunity to learn some more. If you have any questions, we do have some time after the talk for more discussion, so please ask at that point. And from here, I'll let the speaker talk about his own research.
Thank you for the very nice introduction, and thank you for giving me the opportunity today to talk about this paper that we were trying to better understand the quantification of organic aerosol with the Aerodyne aerosol mass spectrometer and aerosol chemical speciation monitor. I would like to acknowledge the co-authors of this paper that helped to make this possible, as well as funding from NASA, the Department of Energy, and Aerodyne. And it wasn't just the co-authors that helped to make this paper possible. What's really beautiful and awesome about the aerosol mass spectrometry and aerosol chemical speciation monitor group is that there's a long-standing collaborative research with trying to understand how the AMS and ACSM work. And unfortunately, because of the number of publications coming out, the Jimenez group stopped updating all the papers that were associated with the AMS and ACSM, but you could see up to 2016 how many papers were coming out. And in addition to trying to collaborate and bring all these papers together to better understand the AMS and ACSM, we have these long-standing users meetings where we come together to better discuss, understand, and improve our understanding of the aerosol mass spectrometer and aerosol chemical speciation monitor. And I'm just building off of all this knowledge that we've gathered as a community. So I'm really riding on the shoulders of giants and just helping to further understand the AMS and ACSM. And what's always surprising and awesome is even with the AMS getting to nearly 30 years as a technology, we're still learning how it's working and improving how it's working to improve our understanding of aerosol chemistry around different regions of the world. So I know the aerosol community is very large and wanted to give a real quick background about why we care about aerosols, but specifically why we care about the chemical speciation and what that means and understanding of how the AMS and ACSM works. So we know from a health perspective that depending on the size of the aerosol, and this was a figure that I found this morning that I think is actually one of the better ways to kind of summarize this, that larger aerosols impact mainly the throat and nose area. Smaller aerosols start getting into the lungs, and depending on the size of the aerosol will depend if it's depositing in the upper portion of the lungs, the lower portion of the lungs, or start crossing over the lungs and into the blood. For a long time, we've just cared about the size and the mass concentration, but we're starting to look and investigate and try to understand what the chemical speciation actually is for these different types of aerosols and how that impacts the health impacts of the aerosol coming into your body. Further, the composition matters for the how the aerosol interacts with the environment, both in deposition and nutrition, as well as water uptake, which can lead to direct or indirect scattering and cloud formation. From a very AMS-centric perspective, though I did acknowledge that there's other types of aerosols out there, the composition can vary depending on your environment and location. And I just gave a very simple schematic of what it can look like depending, again, where your location is, what sizes you're looking at, and with what instrumentation. But the way I have this broken out is from the volatile, non-volatile, or the refractory, non-refractory perspective. Non-refractory from an AMS and ACSM perspective is aerosol that quickly evaporates at 600 degrees Celsius, whereas the refractory or semi-refractory type aerosol or non-volatile aerosol, depending on your community, is aerosol that doesn't quickly or doesn't evaporate at 600 degrees Celsius. A lot of times this is either elemental type aerosol or aerosol associated with larger particles that are dust and salts and metals, whereas the volatile or non-refractory aerosol tends to be organic aerosol, ammonium sulfate or bisulfate, ammonium nitrate, and ammonium chloride. But in order to actually measure these different compounds, there's a lot of different techniques out there. And with today's talk and paper, I mainly focused on the aerosol mass spectrometer and aerosol chemical speciation monitor. So at Aerodyne, we have these, what I like to call different flavors of the same type of instrument, where the aerosol mass spectrometer is more the scientific grade instrument that is a little larger, has better time resolution and mass resolution, and allows you to get the particle size distribution. Whereas the aerosol chemical speciation monitor, both as the quadrupole ACSM or QACSM and time of flight aerosol chemical speciation monitor or TOF ACSM, are simpler in design to allow for long-term monitoring of these volatile or non-refractory aerosol in different locations around the world. And this, we can either measure them as PM1 or PM2.5, and I'll get what that means with the technology that's being used with the instruments. So if we take a step back at both and look at how the aerosol chemical speciation monitor that I have on the left versus the aerosol mass spectrometer that I have on the right operate, they are generally the same technology with a few differences that I'm not going to get into today. But the key parts that matter for how these instruments work so that we can sample the aerosol and in turn matter for the paper that I'm talking about today include the aerosol particle lens that I've highlighted right here. And the idea behind this lens is it's not unique to Aerodyne. It's for any aerosol, any mass spectrometer that is trying to sample aerosol, is that it collects the aerosol into a very tight beam and focuses it so that we can get it to the vaporizer and actually measure the aerosol while also trying to separate the gases. So you can kind of think of it as a way of super concentrating the aerosol above the air background. The next portion that matters that is similar across both instruments is the vaporization and ionization region. So the vaporizer or the heater, as I was saying earlier, is at 600 degrees Celsius, so it's flash vaporizing the non-refractory or volatile aerosol into gases. And then we have a filament that is emitting electrons, and then we have electron ionization of these gases that are formed. And then finally, we have our detection of the ions, either with a quadrupole mass spectrometer or time-of-flight mass spectrometer with a detector to count the ions. What this means is if we look at some of our favorite aerosol that we can see with AMS and ACSM, is if we're looking at like water, or ammonium, or nitrate, or the organics. For example, the ammonium is going to undergo ionization into NH3+, NH2+, and NH+. Nitrate from ammonium nitrate is going to form HNO3+, NO2+, NO+, and etc. And we're just looking at these ions to get an understanding of what the total mass concentration and composition of the aerosol is. But in order to do that, we need to figure out how to translate the ions that we're observing into mass concentration. And that's where the one equation to rule all equations, to rule them all, one equation to find them, one equation to bring them all in the darkness and bind them. And I'm sure that's what Tolkien would say if he was an AMS or ACSM scientist. But the one equation is that to get to the concentration of the aerosol we're observing, we use the ammonium nitrate as our calibration source, which is why ammonium nitrate is here, and the ionization efficiency of ammonium nitrate. And then we have, and that is through a calibration that we do depending on the type of instrument and what type of measurements you're doing, weekly to up to every 3 months. And then we have this relative ionization efficiency. So it's a calibration that compares how well the different components of the aerosol ionize compared to our base compound of nitrate. So for example, ammonium has its own RIE, sulfate has its own RIE, and organics have their own RIE. The CE is the collection efficiency, and we sometimes kind of shorthanded to just the balance of the aerosol, meaning when the aerosol is coming to the vaporizer, what is the chance of it hitting the vaporizer and staying on the vaporizer versus hitting the vaporizer and bouncing and then coming back and having a slower evaporation compared to something that directly hits the vaporizer and stays there. But other components that matter for the collection efficiency, which I'll show later, matters for what our understanding of the organic relative ionization efficiency includes the shape factor. So once the aerosol goes through the lens, what's the likelihood of it staying in the beam or spreading out, as well as what sizes do the aerosol make it through the lens, because some aerosol we're blind to due to Brownian diffusion, while other aerosol impact the lens before we're able to see it. And then the final thing is the number of ions that we're seeing here. And once you use this equation, we can get to the mass concentration of the aerosol observed by the aerosol mass spectrometer or aerosol chemical speciation monitor. For ammonium, nitrate, and sulfate, it's very easy to get the relative ionization efficiency because you can get a standard directly, atomize it, and get its response directly. However, for organic aerosol, which can be composed of hundreds to thousands of different compounds, trying to find one standard or even a mixture of standards to understand what its calibration factor is more challenging, as highlighted by Joel Thornton's review paper in 2020. So some of the early work that Aerodyne did, including with Jose Jimenez, was take various standards and look at how they ionize relative to ammonium nitrate and other inorganics. So what this plot is showing from one of Jose's famous papers in 2003 is if you looked at the ionization cross-section of different surrogate compounds versus the number of electrons in the molecules, you'll see these general trends that the very reduced, aka primary-like aerosol has a slope of 0.35. The more oxygenated aerosol has a slope of 0.24. And then the inorganics, which lie a little bit higher than just pure gases, of 0.15. And if you take the ratio, for example, of the oxidized aerosol to the nitric acid, you get a relative ionization of around 1.4. if you are looking at the pure hydrocarbons, the relative ionization is a little bit higher for the hydrocarbons. But since a lot of the aerosol tends to be more oxidized in state, we've used a default value of 1.4 for analyzing the data and getting to the organic aerosol mass concentration around the world. And this has been further verified in other studies where they looked at other molecules and looked at the ionization efficiency versus molecular weight. And the slope that they found was around 1.4, and that on average, most of the aerosol that they observed was around 1.4, except for a couple hydrocarbon, more primary-like aerosol being slightly higher. Further, we have a huge database of ambient observations to further understand and verify that the relative ionization of organic aerosols was 1.4. So in Jose's 2016 paper that was led by a lot of AMS users, what they did was they looked at the comparison of the AMS and black carbon volume divided by the volume measured by other instruments, and that you see the Gaussian fit is centered around 1 at 2 different urban locations. Further, they looked at the ratio of the AMS organic carbon to a different organic carbon measured by sunset and plotted that versus the primary organic aerosol versus the total organic aerosol. And if the RIE was 1.4, everything would be falling along the 1-to-1 line, but we are seeing a slight increase as more primary organic aerosol is observed. However, it's within the combined uncertainty of both measurements, so it makes it more difficult to say what the RIE should be as we're seeing more primary like aerosol. So in general, if we're looking at urban aerosol, it's been assumed that 1.4 works. However, there's been recent observations where they've been looking directly more at the emissions of primary aerosol, specifically cooking aerosol. So in this paper in 2018, led by Reyes Villegas and James Allen, what they did was they looked at the mass concentration of cooking aerosol measured on a Figaro, which is a chemical ionization mass spectrometer that you collect the aerosol onto the filter, heat it up, and you're able to see how much aerosol was collected as a gas that way, and compared it to the aerosol mass spectrometer organic aerosol. And we see that there was a difference between the Figaro and the AMS, suggesting that there is a different relative ionization efficiency for cooking aerosol. And this was further explored and highlighted by Erin Katz's paper, which was also another talk that was given in, I can't remember if it was late 2021 or mid 2022, where she also discussed differences in the AMS response to cooking aerosol compared to an SMPS measurement of the volume concentration. So some early measurements that were done at Aerodyne that's highlighted in Shu's 2018 paper, they looked at the relative ionization efficiency for different standards versus oxidation state. So how oxidized is the aerosol? And they were looking at measurements on the capture vaporizer, which is CV, and standard vaporizer, which is SV. And they found that in general, there's an increasing trend of RIE as the oxidation state goes down, or as you get to more primary-like aerosol of hydrocarbon-like and cooking organic aerosol. However, it's not a very strong trend because we're also seeing some observations that are still staying around the 1.4 to 1.6 value, and it's hard to draw a line due to the scatter of the measurements right here. So some of the questions that we looked into for this paper is, why is there a large spread in the relative ionization efficiency for organic versus oxidation state? Does the relative ionization efficiency vary across the AMS versus the aerosol chemical speciation monitor, which was not looked at in Shu's 2018 paper? Can other metrics be used to explain the relative ionization efficiency? And is there an easier way to calibrate for organic aerosol relative ionization efficiency instead of having to use a lot of equipment that they used here, or procedures they used here that is more complicated for many laboratories to try to replicate? So the first thing I did was I redid the experiment that SHU did in 2018, but with many new standards. So what this plot is showing here is the results from SHU 2018 in squares, results from Aaron Katz's 2021 results as stars, new standards that I did in blue, and then similar standards that SHU had in orange. And what we're seeing is when we're adding this more information, there's a lot larger spread at low oxidation state. And again, this matters because if we're looking at different types of organic aerosols, such as the hydrocarbon-like aerosol that's directly from tailpipes of cars, cooking aerosol, and biomass burning aerosol, this large spread in the relative ionization efficiency versus oxidation state is hard to explain and capture and to tell the users or people that are using the AMS what the relative ionization efficiency should be. Further, because of the technology of the aerosol chemical speciation monitors, they're not directly measuring the oxidation state of the aerosol. We can estimate what the oxidation state is, but this parameterization that we're seeing here is not going to be very useful for these different types of instruments that we have. So the next thing I did to try to better understand of what was happening, and also can we use different methods that are simpler so that people can start trying to calibrate for the relative ionization efficiency of organics in their laboratory. So first I looked at a range of different secondary organic-like aerosols, which I'm highlighting here with levoglucoxin, xylitol, 1,2,6-hexene triol, mannitol, and threotol. We really love our sugars, versus the measured relative ionization efficiency that I measured for these different secondary organic aerosols. So what's being plotted here is when I mix the sugars in just a water solution, or I did water plus ammonium nitrate with the hypothesis that if there's enough ammonium nitrate in there, the CE collapses to 1, and then you don't have to worry about the different secondary organic aerosol bouncing differently, and it eliminates that uncertainty of the bounce of the aerosol. Then there's a lot of organics that don't want to dissolve in water. So we also looked at using acetonitrile, since that was one of the cleaner solvents that we could use on the AMS. And then doing acetonitrile plus ammonium nitrate with the same question, can we use ammonium nitrate to eliminate the collection efficiency question? And then we repeated these on the quadrupole ACSM and the time of flight ACSM, as well as compared with any results that SHU had in his 2018 paper. So first, as I said, I'm just showing the results from the sugars that we measured, which are our secondary organic-like surrogates that we use to look at. And what we found is the variability with standards with and without ammonium nitrate, so the blue and light blue, was on order of 2 to 13%. So what this means is ammonium nitrate can be mixed in with sugars in order to better measure the relative ionization efficiency without worrying about bounce. The key aspect is it has to be sugars or other things that are non-acidic. If you try to do this with acidic secondary organic aerosol precursors, such as carboxylates and things like that, they start reacting with the ammonium nitrate and change the amount of nitrate that we're observing, and it will lead to a relative change in the RIE and the amount of ammonium you're seeing, so it leads to larger uncertainty. So this can only be done with non-acidic sugar-like secondary organic aerosol-like precursors, or pure POA type precursors, anything that doesn't have carboxylates in them. Then if we look at the behavior between water solution versus acetonitrile solution, so if you're looking at the dark blue versus the dark brown, we're seeing a variability of 8 to 10%. So this is showing that you can use water or acetonitrile depending on what is the best solution to dissolve your precursor against, to make it a simpler procedure for people to try to reproduce and do in the laboratory. And then finally, we saw that there was less than a 25% variability across our instrument flavors, aka the AMS versus the quadrupole and TOF ACSM. So for secondary organic aerosol like precursors, everything is behaving similarly, and it's allowing us to, as I'll be showing later, get a better constraint and understanding of how relative ionization efficiency is working in the AMS. What was interesting was when we look at the primary organic aerosol like precursors, we see very different behavior as being highlighted here. And what we see is if you compare AMS to AMS for both SHU and what I did in our study, we're getting somewhat similar to slightly different results. But the larger difference is when you're comparing AMS to the ACSM, the TOF ACSM as the light scion, and the Q ACSM in the darker scion. So what's happening here? So what we know from Sally's 2011 work is that the Q-ACSM has an MZ-dependent ion transmission efficiency that starting at around MZ50, the MZ-dependent ion transmission starts decreasing until about MZ150, where it flattens out to being about 10%. And this is something that is regularly measured as we have a naphthalene source in the Q-ACSM that allows us to correct the data so that we have the best approximation of the MZs that we're seeing for aerosol that has higher MZs. So I was wondering, do the other instruments have different MZ-dependent ion transmissions? Since it hasn't been well documented for our different flavors. So I put a naphthalene source in all the different types of AMSs and ACSMs we have to see what does the ion transmission look like. So as comparison, again, the red line is the Q-ACSM, and then the block of data that we have right here is for the compact time of flight AMS, which is similar to the mini or miniature AMS, as well as our TOF ACSM and our newest instrument, our time of flight aerosol chemical speciation monitor with the extended resolution, or TOF ACSM-X, which that paper will hopefully be submitted next month to ASNT, are all falling on a similar MZ-dependent ion transmission. And we think this is a combination of both the type of time of flight as well as detectors that are being used in some of these flavors that are leading to improved MZ-dependent transmission compared to the Q-ACSM, but lower MZ-dependent ion transmission compared to the high-resolution time of flight aerosol mass spectrometer in black and the long time of flight aerosol mass spectrometer in gray. Note, since we were doing this with naphthalene, we were restricted to what MZs we could look at. So we were assuming a linear fit all the way to where it reached zero, where there could be different dependencies on the actual ion transmission, MZ-dependent ion transmission for these different instruments after the highest peak for naphthalene. So what does that mean if we start looking at real world samples? So what I did was I took the different types of factors that have been observed around the world, hydrocarbon-like OA, biomass burning OA, cooking OA, and cold combustion OA, and looked at what does the MZ-dependent transmission mean for how much of the MZs we're seeing for these different samples. So if we look at hydrocarbon-like OA first, the mass spectra that I'm showing here is from an aerosol mass spectrometer. And then if we compare the total sum of the sample that we're seeing of the ions without the MZ-dependent correction that we use for the Q-ACSM, we're seeing the Q-ACSM, for example, is observing about 70% of the ions without the correction. The TOF ACSM, TOF ACSM-X, and CTOF and mini AMS are seeing around 80 to 90% of the ions, with the HTOF and LTOF seeing 100% of the ions, since I'm taking the mass spectra directly from those instruments. So we looked at this also for biomass burning, cooking, and cold combustion OA, and you're seeing that it varies for the Q-ACSM and TOF ACSM of 60% up to around 80 to 90% of the ions being observed, depending on what type of OA we're looking at. Again, note that the Q-ACSM includes an MZ-dependent transmission correction, so the final data won't be saying you're missing 60% of the MZ since we are correcting for that. But some key things that will come up later as important is POA has a lot of signal at high MZ or mass to charge ratio. There may be some underestimate for the correction that we're applying, but the TOF ACSM, et cetera, does not correct any of the potentially missing higher MZs here, since we don't have a correction factor and we don't include a naphthalene source to do a correction factor. And this is only really important if you're directly measuring only sources. If you're measuring a mixture of sources, it's not as important. So if we do the same type of exercise for our less oxidized OA or fresher secondary organic aerosol and like pink versus our more oxidized organic aerosol or more aged secondary organic aerosol and dark pink, we're seeing that there's higher amount of signal that we're collecting with these instruments, and that's directly related to there being more ions at lower mass to charge or MZ values. And in general, you would think that this is more representative of the atmosphere. And what I mean by that is if we look, for example, my 2021 paper where I looked at urban secondary organic aerosol production, except for New York City during winter time where there was a lot of biomass burning and the primary organic aerosol was 50% of the total organic aerosol observed by the AMS. Most of the primary organic aerosol in these various urban locations are around 0 to 33% of the total organic aerosol. So you're not really missing or losing a lot of data information just because when you're measuring from an urban background site where everything's well mixed and the primary organic aerosols had time to evaporate and or undergo oxidation, it starts looking more like secondary organic aerosol, and we're very good and sensitive at seeing the secondary organic aerosol. But if we go back to these mass spectra and we see that the secondary organic aerosol generally has most of its signal at low MZ, while the primary aerosol has a lot of signal at high MZ, can we use this feature to help better explain organic aerosol relative ionization efficiency? And in particular, if we take MZ50, because that is at the ion that the QACSM starts decreasing its efficiency, MZ-dependent efficiency of seeing ions. So what I did was I went back to all the samples that have been collected for various studies and looked first at the PMF factors as well as the bulk organic aerosol, at how much of the signal of the aerosol is observed at MZ50 or less. So the FMZ50 is the total number of ion signal at MZ50 or less divided by the total ion signal you're seeing for organic aerosol. And for the oxidized organic aerosol, both the more oxidized and less oxidized organic aerosol, so the less aged and more aged secondary organic aerosol, we're seeing a large fraction of that at around 50% or more of the signal is at MZ50 or less. And that corresponds to urban background sites that you're seeing around 50 to 60% of the signal being at MZ50 or less. And then when you go to rural remote locations where you're away from primary sources and things are well oxidized, you're starting getting to 65 to 90% of the bulk organic aerosol having most of its signal at like MZ44, MZ43, so things below MZ50. But for the primary organic aerosol, we see that a lot of the signal, as we saw with the mass spectra, tends to be at higher MZ values, and we're seeing that it's less than 50%. So what does that mean if we do this for the surrogates that I've used in the AMS as well as prior studies? So what I'm going to be showing here is, again, the measured relative ionization efficiency for organic aerosol versus this F sum of MZ50. So if we start here at the where most of the signal is below MZ50, so again, you're seeing a lot of the signal at MZ40, MZ43. For what I measured in the study, which is the colored circles, we're seeing it's staying relatively flat at this value and at high oxidation state, which is why I have it colored by here. And we're seeing similar structure for the quadrupole ACSM, time of flight ACSM, as well as measurements from the work that Shu did in 2018 and the measurements by Katz in 2021. But as soon as you go above around 0.65% of the, when you go below 0.65, 65% of the signal being at MZ50 or less, you start seeing this general trend of increasing relative ionization efficiency for the surrogates that fits with all the measurements from prior studies with a couple important outliers. So in general, we find this split in the population that for secondary organic-like standards, which is representative of background urban sites and our oxidized organic aerosol, the relative ionization efficiency on average was 1.23 plus or minus 0.62, which is the value of 1.4 as well within the uncertainty that we were able to constrain here. And then for primary organic-like standards, we see that the relative ionization efficiency is greater than 1.4. Again, this is when more and more signal is above MZ50. We're also found that independent studies agree with the fit as well as some of the outliers that we observed. For example, for the polycyclic aromatic hydrocarbons, both in oils that Slavic measured in 2004 and independent PAHs that I measured as part of the study that were not included in the fit, we see this very independent feature that they have relatively low relative ionization efficiency compared to how much of the signal is above MZ50. And this is due to the structure of the rings that are making it relatively harder for the rings to break apart when you do electron ionization impact, as well as the fragment thermal decomposition. And also due to those rings, they need lower total ionization efficiency to be observed. So the outliers for those are here. And then some of these outliers right here are due to similarly measuring aromatic type structure compounds that lead to similar type of features. Then the saturated hydrocarbons that we measured up here that are much higher, these were a lot harder to measure due to their volatility and how much was necessary to even get a good signal. So they're not included as part of the fit, and we think that's part of the explanation of why they had a higher relative ionization efficiency compared to everything else that was part of the fit. But as I've been stressing, most urban OA, if you're measuring in an urban background site instead of directly behind a tailpipe or right out of a vent of a cooking area or out of a chimney, is in the range of the relative ionization efficiency used as the default for organic aerosol of 1.4. And then Anna Millbrook sent me some more data from the paper that they just published in 2023. And in general, again, we're seeing very similar results for the relative ionization efficiencies that they measured, that everything is lying within the 1.4 value. And then the outliers right here are from nitrocatechol, which is, again, an aromatic compound that doesn't behave like everything else, so it has a different relative ionization efficiency. So cool, we have this better understanding of what is leading to the relative ionization efficiency, but we're not comfortable as telling users that this is something that needs to be used as a default for AMSs and aerosol chemical speciation monitors for a couple of different reasons. One is primary organic aerosol can be a different population than secondary organic aerosol and other secondary compounds. So this is from Mangela's 2004 paper where they were sampling behind diesel buses, and they found that the primary emissions of organic aerosol behind diesel buses was at a different diameter than sulfate. And this external mixing of aerosol is important because we use the bulk aerosol to calculate the collection efficiency. If the primary organic aerosol has a different collection efficiency than the secondary organic aerosol, it's going to be hard to quantify that due to their external mixture. So as an example, cooking aerosol looks like it has a collection efficiency of 1, meaning when it hits the vaporizer, it stays there. but it's hard to be able to quantify that when we're looking at bulk aerosol instead of being able to separate the primary versus secondary aerosol. Similarly, another quantification aspect of primary organic aerosol is going back to the lens transmission. So what aerosols make it through that aerosol lens that we use to get the aerosol into a tight beam to sample it. A lot of primary organic aerosol tends to be at small sizes where we also have lower efficiency of observing those aerosol because of Brownian diffusion before we get to about 70 to 80 vacuum aerodynamic diameters. So there's always going to be this question of how much the aerosol we're not observing due to it being a small size and we're losing it through the lens. So what we are suggesting is to look at the FMZ50 to suggest there might be a different relative ionization efficiency, but not to apply it because there could be offsetting aspects to the quantification of primary organic aerosol due to the CE external versus internal mixing and lens transmission, which is all important again for the main equation that we use to convert the signal of the ions to the mass concentration of the aerosol. And if we go back to urban measurements where we compare the AMS to other measurements, we generally see within the combined uncertainty of all the measurements that the AMS is agreeing with these other measurements, suggesting again that in an urban background site, as I've been highlighting, a value of 1.4 makes sense. It's when you are really measuring primary sources with nothing else that this can start becoming a quantification uncertainty, and having SMPSs or other measurements to help better understand what the organic RIE might be will be useful. So with that, in conclusion, we find that the thermal decomposition of electron ionization and fragmentation and MZ-dependent transmission all control OA quantification. And that's all important because since all these steps are independent and lead to different ions altogether, it's hard to a priori calculate and create a model to predict what the relative ionization efficiency of different organic aerosol constituents are. But what we found is secondary organic aerosol standards are consistent across different AMS and ACSMs and with different solutions and methods to quantify what the relative ionization efficiency is. That POA standards were a little more inconsistent, and it's related to the MZ-dependent transmission curve of the different instruments. If we combine the information that we have with the mass spectra with the different organic aerosol types and the MZ-dependent ion transmission, it's provided a new way to look at OA quantification, in particular that we're seeing that if most of the signal is below MZ50, the relative ionization efficiency of 1.4, which is the default that's used in the software, is applicable. And this is for urban background sites to more aged organic aerosol. But if we're looking directly at a source, you should look at how much of the signal is above MZ50 to gain insight that the relative ionization efficiency might be higher, but do it with caution, again, because of the caveats about external versus internal mixing, which is necessary for the bulk collection efficiency that's calculated, as well as lens transmission. And with that, I'll take any questions.
Thank you so much for an amazing talk. We do have plenty of time for questions. Anyone feel free to just shout out or do the hand raise emoji thing with the Zoom controls.
So I see there's a question in chat for RIE of biogenic SOA. This again will depend very much on the oxidation of it. But the rural remote that we had right here was for biogenic areas such as Southeast United States, the forested site in Colorado and places like that. And we were finding that the FMZ was greater than the 0.65, 0.7. So we would expect it to be around 1.4. Mind you, if you're doing chamber experiments where there could be higher seeds, so things can condense at a lower oxidation state, so it hasn't oxidized as much as what might be representative of the atmosphere, then the relative ionization efficiency might be higher. And this is where comparisons with an SMPS, as well as looking at the fraction of ions below and above MZ50, will give you insight of what the RIE would be. But I would say for atmospheric measurements, the RIE is most likely going to be around 1.4. And yes, it is a similar type of idea that it depends on what the loading is and how oxidized the material is before it condenses.
I have a question as well, while other people think of some. I was wondering whether, so you were talking about how the RIE is determined, and how the collection efficiency is determined, and I was wondering about the bounce factor. So do the different types of aerosols, like primary or secondary or cooking aerosol, is there like a stark difference in the bounce factor that you can see between those, and what properties of an aerosol would impact the bounce factor?
So unfortunately, from an organic perspective, we haven't really looked at bounce as much because it's hard to find good surrogates to do this, as well as a question of how much the aerosol we're seeing due to lens transmission and somewhat due to shape factors. Some measurements of the cooking aerosol where we know the sizes are large enough that we don't have any lens transmission impacts, it looks like they have no bounce, that they have around a CE of 1. And this is more related to like oleic acid or other types of these acids that when you look at them as standards, they're very wet, viscous materials. So when they're as particles, they're wet. And when they hit the vaporizer, they're just going to stick. For things that are not cooking aerosol, we would have to try to find standards that we are size selecting so that we know there's no issue with it going through the aerosol lens in order to really start quantifying the bounds. And then it becomes a whole new exercise because you either need to have an AMS that has a laser on it so that you can see how many particles are making it to the vaporizer versus how many particles are coming off the vaporizer, or doing event trigger, which is another quantification method that's available with the new aerosol mass spectrometers. And it's even more complicated with the aerosol chemical speciation monitors since they're missing a lot of this information. So it's future work that needs to be done, basically.
All right, well, if no one else has any questions,
I
I'm
just explained
sure.
everything so well.
Yeah. I mean, you wrapped it up perfectly. No more research can ever be done on this. That was a perfect summary. But you can like try to DM Dr. Nault if you want to ask something later. Or I'm sure you're reachable through email if anyone has anything come to mind. But let's all thank Dr. Nault again. That was an amazing talk. I learned so much. And we really appreciate you being here. Thank you.
You're welcome.